With matrix equations, the basic thing looks like this, right? It's really easy when you're adding and subtracting because there's not much to that. If I'm adding, a plus x is equal to b, I can just subtract a from both sides. There's nothing magical about that. However, here, normally what we would do is divide both sides. We don't have division in matrices. So what we would do is multiply both sides by the inverse of A, because that we do have. This would become the identity matrix. And so X would actually turn out to be whatever the product of these two turned out to be. Now, one of the things we know, if you'll recall about finding the inverse of a matrix, is it's 1 over the determinant times the adjoint. And the adjoint is where you switch those and change the signs of those. Okay. And the reason I'm pointing this out again is that you can tell whether or not a matrix is going to have an inverse by whether or not the determinant is 0. If the determinant is 0, then you're not going to have an inverse. So let me give you an example here. If you look at this, you can pretty much tell that if I take this 2 by 2 matrix, 3, 2, 5, 1, and I multiply it by x, y, right, that matrix. Right, this is a 2 by 2 matrix. This is a 2 by 1 matrix. And we know they can be multiplied together because those two numbers are the same. And we know that the result will be a 2 by 1 matrix. And because of our equation here, we want the 2 by 2 matrix to turn a 2 by 1 matrix to turn out to be that. Now, when I say these two are the same, let's take a look. 3 times x plus 2 times y, that would be the first element in the 2 by 1 matrix. And 5 times x plus 1 times y will be the second element. And as it turns out, that's this. And then over here, this is 16 and 22. So these things need to be equal to each other. That's what this equation says. So now the next thing we're going to do is try to figure out what's the inverse of this matrix. If I multiply 3 times 1 and subtract 5 times 2, I'm going to get 3 minus 10, so that's -7. And the adjoint here, I'm going to switch these. This will be 1 and 3, and switch the sign of these. This will be -2 and -5. And I'm going to multiply this by this matrix here, 3, 2, 5, 1. And this matrix here, which is x, y. And then on this side, I'm going to have 1 over -7 times the adjoint, 1, -2, -5, 3, times this, which is 16 and 22. So over here, all of this sort of goes away. Multiplying all of this together gives me the identity matrix. So on the left, all I have is x, y. On the right, what I'm going to do is multiply the two matrices together first and see what I wind up with. Okay, so I'm going to leave this in here. And I should wind up with a 2 by 1 matrix. 1 by 16 plus -2 by 22. So it's 16 minus 44, and that's negative 28. Okay. And then I'm going to do negative 5 times 16 and 3 times 22. That's negative 80 plus 66. And that turns out to be negative 14. And then if I multiply both of them by negative 1/7, I get x, y is equal to 4, 2. So we can plug those back in to see x is 4, y is 2. Going back up here, 3 times 4 is 12. 2 times 2 is 4. 12 plus 4 is 16. Over here, 5 times 4 is 20. Y times 2 is 2. I mean, 1 times 2 is 2. So it's 22. So this actually is the solution. Okay. Now, I did those in the context of a system of equations, but there's no particular reason why we couldn't do the same thing we did over here. And I could give you something like, 1/4 matrix A times X is equal to matrix B. And then you'd have to multiply both sides by 4. And then you'd have to multiply both sides by the inverse of A. And you have to remember when you're doing this, that multiplication is not commutative among matrices. So if you're multiplying on the left here in order to make the A go away, then you have to do the same thing over here. Do it on the left. Right, and what I was starting to say is if you're doing this on this side, then you're going to have to come over here and do the same thing on this side. Because you can't switch them around.